All right, so this is the Unit 3 energy review, and like I said in class and everything, I'm going to really just try to focus on the main important stuff and try to narrow everything down into a package that you could understand. First of all, the whole unit is called energy, and so it's good to know what energy means. Energy is just the ability to do work. So I'm going to write that down, the ability to do work. Energy is just, it just gives us the ability to do anything. Mostly in terms of kinetic energy is what we talk about. So like you could store energy. So there's stored energy. That's your potential energy. So there's elastic potential where you store energy in a spring or rubber band. And then they're stored gravitationally, where you just lift things up high, and then they're going to do something, and that something is move. And so before I go on with that, let me just kind of break this down a little bit. So the stored energy is either, like I said, gravitational, and that's our PEG, and that has to do with height. I'm going to spell this wrong. Probably right. Then the other option is our elastic. It's all both potential. So potential energy, elastic. And that has to do with something like springs or rubber bands or whatever. So you're storing energy either by lifting something up to a height or in a spring or a rubber band. So now, like I said, what are we doing with that energy? Well, we're going to use it and we're going to create some motion. And that motion is just kinetic energy. So it's going to be used. And like I said, we call that kinetic energy, or KE, and that is motion or movement or whatever. Okay, by the way, whenever I look over there, that's just me looking at the chat to see if anybody has any questions. So if you do have questions, you could chat, let me know, or you could use the Remind app, and I will try to respond to them as quickly as possible as soon as I notice. So so that's what energy is. It's the ability to do work, and you could store it and you can use it. So that's how it breaks down. And one thing, and this is sort of a minor thing, you don't even need to worry about it too much, but when you use it, when you use the energy to do something, we call that work. And so it's basically using energy, and in our case, we're going to really simplify this and just kind of, like I said, stick to what we would talk about: to move a distance. So you have to be able to move. Let's get that glare out of there. Ish. That's a little bit better. So it has to. We're going to use energy to move a distance, and if you remember, there was an equation about that where basically, if you do work, you are causing a change in energy. Okay, so basically, work is change in typically kinetic energy. So if something moves, you've done work to it. The other definition we had kind of goes along with that definition of work is a force over a distance. And that distance is sort of important, because if you don't move it, that means the distance is 0, which means you've done no work. So there's a question on the review guide that talks about if somebody hands you something, you're sitting there holding it, if you're not moving that thing, you're not doing any work. So no matter how heavy something is, it has to move a distance in order for you to do work. That's displacement times the force. You have to move a certain distance to really get work done. Otherwise, you're not doing any work. All right. There's some mention of power. Again, this is sort of a minor. These are all minor equations. and you're not going to see too much. You'll see it on the review guide. But power is just in reference to how quickly you use energy. The amount of, here, it's work per time, which is just how much work are you doing in a certain amount of time. So if you use energy up quickly, you have more power. You're using more power. You're exerting more power. If you do a certain amount of work over a short period of time, it's a lot of power. If you do it over a long period of time, it's just not as much power. So it's just work divided by time. Now, before we go much further, I'm going to say that, and you're watching this, so that means you care about your grade. This little data table up here is like the key thing. Make sure you have all those down pat. You need to know what these symbols are, what they represent, the unit, so you can identify them in a question, and more specifically the unit symbol, because a lot of times it'll just be the symbol most times. So make sure you've got this, make sure you have a full understanding and remember this. So write it down, rewrite it if you need to. All right, get it. If you're not sure about these things, your best bet is to go to the key, which is linked on the OneNote, write these down, and then rewrite them in another place, and maybe do it again. Try to do it at some point without looking, or looking at the answers, and see if you could get the answers for yourself. All right, so this is paramount. If you don't know these things, you're going to have a really bad day when it comes to the test or moving forward with this unit. All right, so key thing right away is make sure you got that. All right, so that's basically it when it comes to work, energy, and that kind of stuff, power. Again, these are mentioned on the review guide, and we actually have a couple questions. I'm going to get to those in a minute. Actually, might as well just do that now. Let's take a look at number 9. There we go. So, I mean, really quick, just a quick application of that. How much work was done against gravity by the gorilla? So whenever you see the word gravity, you just got to kind of think about gravity goes up and down. And so you don't even need to do that with this question, because if you look, you can see that we got 2,000 newtons, and that's a force. We've got him climbing 5 meters in 40 seconds. We want work. And if you got the equation down, work is just force times distance. All right. So literally all you got to do is multiply that force times that distance that he climbs. Okay. Nothing more complicated than that. And this comes with understanding and knowing that, and recognizing that N is newtons, is a force. M is meters, that's a distance or displacement. And 40, which didn't even come into play here, seconds, is a time. There's no time in this equation. So it wants to know how much work is done. What's the equation for work? Remember, you'll be able to, we're going to make a note card the day before the test. And so one thing you'll be able to write down is all this stuff, anything you want. But you'll be able to write down work is force times distance, and anything else you need. You're not going to have this memorized. So that's one thing you can do. All right. Power then is just going to use this equation. You just take the work. Here's where you actually do power is the work, which I don't remember. Oh, I got the key right here. Number 9, 10,000. Yeah, well, that makes sense. Okay. 10,000 joules, and you're going to divide it. That's where the 40 seconds comes in. Okay. So that's where you divide it by the work divided by the time, you get your answer. All right. So fairly simple equation once you get a hang of it. But once again, you got to get the hang of it, and you got to have this. Got to have this down pat. You got to be able to recognize what all those numbers are. In fact, you won't be able to do this on the test necessarily because it's going to be on the computer, but on the practices at least, I mean, like I would just go like circle, like you don't have to underline it, but this is going to be your force. This will be your displacement, and this could be your time. So that comes down to if you recognize those units, then just identify them right off the bat. Okay, write them down, underline them, put a little note like that. All right, just so that you know what's what, and then just figure out what formula to use. Okay. So that's work, energy. There's Nothing on the chat yet, so no questions. So I'm just going to go forward. The next, and this we're getting into the biggest part of the unit, the most important part, and this is the types of energy. I already mentioned them. Gravitational potential, PEG, elastic potential, PEE. Both are stored energy. Now, one is all about changing the height, and the other one is involving springs. Then there's when energy is being used to do something, and that's kinetic energy. KE, and that is going to be anything in motion. So now this right here is the most, it's the biggest part of the unit. All right, so make sure you are 100% familiar with this stuff. I'm going to start with, I'll go in the same order as I went up there. So PE, what did I start with? G? All right. PEG, I mean, I'm writing this down. Hopefully this is not news to you, is MGH. Okay. Now, one little caveat, one little thing to keep in mind, and I can write it in orange, I just did that, is this G is a constant, and it's always on Earth going to be 9.8 newtons per kilogram. All right, so that is like a big thing to make sure we're going to write down on your note card. All right. You don't want to have to sit there and be like, oh, was it 9 point? Oh, crap. You know, we're going to write that down. But we're going to use it so much that hopefully it'll come to you. You won't have to have it on your note card, but you're going to, just in case, you're going to have it on your note card. So that's the one, that's the big important one. And this one has to do with, again, there's the height I was talking about earlier. And this shouldn't be any news to you, but this is a review, so we're reviewing. M is mass, and G we just said is that. So you multiply all those three together, and you're good. Now, the thing you have to be able to do is if I give you, or somehow you get the energy and you have the energy, and maybe you have mass and you have gravity is always 9.8, can you find the height? All right, that is important. So be able to rearrange these to solve for any variable. All right, typically in this case especially, it's going to be easy. You just divide both sides by, you know, whatever you're not trying to find. So if you're trying to find height, you would divide both sides by mass times gravity. And double check your ability to put that in the calculator correctly. A lot of times I see trouble where the order of operations isn't done correctly. For example, let's say I wanted to solve for height, because I just use that example. If I wanted to solve for height, so the question was, how high did something end up? Well, then it's going to end up being, I'm just going to write this as if I just divided both sides by mg. All right, that's going to end up being the equation you're going to use. You got to know how, and again, I only say this because so many people make this mistake. You got to know how to make your calculator do the multiplication first and then divide. And the best way to do that, I mean, there's a couple ways to do it, but probably the quickest way to do that is just to make sure that you put parentheses around everything on the bottom like that in your calculator. Okay, because it is a multiplication and then followed by the division. You got to get order of operations. All right, that said, the second equation is going to be, make sure I'm on the screen here. What I have up here, elastic. So going back to my little purple list, elastic potential energy. Once again, this shouldn't be any new thing to you, but this is review, so we are reviewing. So potential energy elastic is all about springs. That didn't help. And that is 1/2 times K times D squared. Where's my little green pen? K, not to be confused with KE. This is not kinetic energy. This is just K all by itself. It's a constant, and it is confusing, but it is what it is. You just got to get over that. K is the spring constant. And constant. Sometimes, a lot of times, you're going to see it referred to as the K value because literally that's what it is. It's just how stretchy is it, right? How, stiff, stretchy, whatever you want to call it. G. Okay. How stretchy is it? The higher the K value, the less stretchy it is, the more stiff it is. In fact, there's a question on the review guide about that. Number 14 on the review guide. It says, which spring would be more difficult to stretch? A spring with a K value of 20 or a K value of 40 newtons per meter? That's just total review. I'm going to pause a second. You try to decide. Okay, 40 is the answer because it takes 40. It's going to be twice as hard to stretch. All right, because it has the twice as big a K value. It's literally how many forces does it, how much force does it take to stretch something a meter or compress it a meter? So that's what K value is all about. And just like with the other one, you had to be able to solve for anything, any of those values, either K or D. So you might have the energy and you know the distance that it's stretched. You had to be able to tell me what is the K value of the spring. We sort of did that as part of the lab we just finished up. But that's definitely something you should be able to do, is just, again, rearrange this. I'm going to get into dealing with this squared when I talk about the next thing, because that's a little bit more common. This one is kinetic energy. And it looks very similar. 1/2 mass times velocity squared. All right. These are the three like heavy hitters of this unit. So make sure you got these down pat. Make sure you know how to work with them. And just like before, you might get asked how, you know, like you'll have the energy, how much, what's the mass of it, and or what's the velocity. You might be able to, you're going to have to solve for any one of these three things if you're given the other two. So the most common one that we have trouble with, I should say, is if I were to ask how fast. So how fast is this thing going? Like maybe at the bottom of a hill, or in our case with the spring, the toy gun thing with the dart gun. Like how fast is that dart moving when it comes out? If we know how much energy it has, same idea. And in this case, just understand you had to divide both sides. I'm going to work it out really quick. So we're going to divide both sides by 1/2 m. There's other ways to do it. You can multiply both sides by 2 and then divide by it, but I'd like to do it all in one step. So kinetic energy divided by 1/2 m is equal to v squared. All right. And now, because unlike this one up here where we didn't have a square, we have a square to deal with. If we were trying to solve for mass, we wouldn't have a square to deal with, but we've got a square to deal with. And so since we've got this little square right here just sitting there, we can't leave that alone. We have to undo that. And the only way you undo a square is to take the square root. So I'm going to take the square root of both sides. So I'm going to do, this yellow doesn't work. Oh, there it is. The square root, does that even show up? Kind of. But whatever I do to one side, I have to do to the other. And so that square root is going to cancel out the square. And so I am left with the square root of kinetic energy over 1/2 m is equal to the velocity. So just know how to do that, or at least be aware how to do that, or maybe even just write that equation down, because that's basically what you got to do. That's never going to change. If I ask for velocity, and you know, if you want velocity and you know the kinetic energy and the mass, this is literally how you're going to do it every single time. So this is something you can write on your note card, possibly, and just have ready to go. Okay, just be ready to use it. Okay, but that said, these are the three big equations that you're going to want to have handy and know how to use. All right, so where are we at with time? 20 minutes. So far, so good. So let's take a look at that. I'll uncover that in a second. So let's look at number 10 really quick on our practice here on our review guide. So we want to know the gravitational potential energy. So again, you just have to recognize what it's asking for. It's asking for gravitational potential energy. So PEG. We have a 0.8 kilogram baseball. That is our mass. That is 12.6 meters above the ground. So meters tells us that is our height, our distance in this case, because we're talking about gravitational potential energy. So you got to keep the context in mind. And so all you got to do is mgh. So mass is going to be the 0.8. G, we already said, is 9.8. That's always 9.8, so that's a constant. And our height is 12.6. Just multiply those three numbers together, you get your answer. Check the key to see if you got it right. Number 11, it wants to know the kinetic energy of a 0.8. It's the same idea, but now we are, so this is going to be the mass, and we have a 15 meters per second. 15 meters per second, hopefully you are like, oh yeah, that's just velocity. I know that. Okay, because it's velocity. Meters per second. Remember, go back to make sure you know how to do this thing. All right. So for this, it wants kinetic energy. So it's literally just going to be 1/2 mv squared. You only square the velocity. You don't square the mass or anything like that. Just the velocity multiplied together. Get your answer. Again, try it out. Check the key. All right. Yeah. So. All right. So far, so good. 13, we're moving on to our other one, and we want to know how much energy is needed to compress a 0.4 meters, compress a spring 0.4 meters if it has a spring constant of 40 newtons per meter. All right, so it doesn't actually say how much potential kinetic, how much elastic potential energy. It just says how much energy. But you're going to use your brain because you know you're smart, and you see that they're talking about springs. Oh, this must be the PE. The elastic potential energy. So you're just going to know that. And in fact, let's just, there it is. Okay. You know this is going to be 0.4 meters. That's some sort of distance. In fact, you look at your equation. Oh, that's going to be the lowercase d. And there's your spring constant. And your spring constant, again, well, even process of elimination, that's going to be that little k. Okay, not kinetic energy. That's the k value. That's this k right here, the spring constant. Okay. So once again, plug that into your calculator. See if you can solve it. Check the key. See if you're right. If not, talk to me tomorrow. All right. So that's that. Pause here. Then move on. Number 15. This is kind of a big one. In fact, I'm going to underline this in red. Law of conservation of energy. The law of conservation of energy tells us that energy cannot be created or destroyed. It can only change shape, or change form, not shape. So it can change from kinetic energy into one of the potential energies. It could change from potential energy into kinetic energy. In our foam, our Nerf gun lab, the energy changed from elastic when you pulled the spring back and you heard a click. That was you pulling a spring, and that stored energy. Then it changed from that spring energy, elastic potential energy, into kinetic energy. So the dart started moving. And if you shot it up into the air, it slowed down and slowed down and slowed down and eventually stopped before it started coming back down to Earth. And so as it got higher and higher and higher, it lost kinetic energy. It slowed down, but it gained potential energy, gravitational potential energy. We did the energy skate park lab, so it's all like that. It showed the bar charts. In fact, later on we're going to do bar charts in a couple minutes. So the basic, whenever you see the word total in terms of energy, the total mechanical energy stays the same. It stays the same. The total will stay the same. That's just, keep that in your head. The total stays the same. I got that capitalized there for a reason. All right, it stays the same. And that's going to help us with some of our questions. In fact, 16, 17 are going to be like that. So, in fact, let's just kind of move ahead. I'm going to let you do 16 and 17 on your own because the one I'm going to show you is more complicated than those. In fact, let me just scooch that out of the way. Get this right up here. So 18 is the big one. And I would recommend that before you watch me do this, or at any time, only watch this to get unstuck, because you need to be able to do this on your own. All right, so watch, get a direction if you need to, and as soon as you see what's going on, stop this video or look away or whatever, and try it. Like, try to finish on your own, because watching me do this and following along is mildly helpful, but you need to be able to do this by yourself. So what is the potential energy at the top of the ramp? Okay, now you read the situation. You got a skater, 60-pound skater, 60 kilogram skater, pushing herself down. She's up 15 meters high, and she starts out at 5 meters per second. All right, he doesn't push himself anymore, and he just coasts for the rest of the time. He reaches the bottom of the ramp, 0 meters high. He comes back up to the next hill, but only goes up 12 meters. All right, I'm going to be honest with you, this should not be in there for now anyway, or at least at the end, for reasons. So the potential energy at the top of the ramp, that is going to be, now you could list all this stuff, and I'm just going to probably list it once just for the sake of time. But if you go through 60 kilograms, that's going to be mass. So M, 60 kilograms. And I got the lines here to kind of help us out. I'll show you what I mean. 15 meters, well, that's going to be the height. Excuse me, the height of the hill. Height of the first hill. Ramp. And we want to know the potential energy. So now, you might have already jumped ahead a little bit. You're like, well, Mr. Jern, PEG is what we're looking for. I just need mass and gravity and height. And you're right. So let's just do that. So we got PEG is equal to the mass, and he is 60 kilograms. Gravity is 9.8 newtons per kilogram. And I didn't give myself enough room, so I'm just going to just bleed over here. The height is 15 meters. All right, so that's about it. I plug all that in, and 8820 is what I got. The units all kind of cancel out, and we're left with Newton meters, which is another name for joules. So I'm gonna put a little box around that just to kind of keep it, so I know that's the answer. Okay, so we figured it out, and all we needed to know was the initial height, okay, at the top, and his mass. Now I want to know the kinetic energy at the top of the ramp. You might be tempted to say, well, it's at the top, he must not be moving at all. But you got to read it carefully, so watch out for this. It says he pushes with an initial velocity of 5 meters per second. That means he's got velocity, meters per second. And we know the kid's mass is 60 kilograms. And why am I writing those out? Because I already know in my head that I need to find kinetic energy. All right, it wants to know kinetic energy, and I know that kinetic energy is 1/2 mv squared, because it's not the first time I've done this. So it's like, well, I know I'm going to need these two things. So I listed them out, and then I just plug my numbers in. So this is at the top of the ramp. Kid's energy is 1/2 or 0.5 times 60 kilograms times 5 meters per second, and that is going to give me an answer of 750 joules, if I did that correctly. So 30 times 5. Yeah. Let me double check that. So 0.5 times 60 times, like Mr. Jern, yes, I know. So guess what? I made the mistake that a lot of you guys make. I said it here, but I didn't do it there. So watch out for that kind of thing. That's still the correct answer, by the way. I had already figured it out, but I didn't write it. So don't ever forget to square it when it says to square it in the equation. All right. So square it if it says square it, and don't forget that. So I'm going to put a little box around that as well. 750 joules. Now the mechanical energy at the skater at the top of the ramp. It doesn't say the word total, but guess what? it wants to know the total mechanical energy. And the total mechanical energy is just you add them all together. So I'm going to write this somewhere on TME. The 4 little lines here are kind of messing me up, but that's okay. It's just going to be the PEG plus the kinetic energy plus, I mean, we don't have any, but I'm going to write it down there just because anyway. The elastic potential energy, what we don't have. So that is going to be my 880 20 plus kinetic energy is 750 joules plus 0 because we don't have any springs involved. And so my total is going to be, and this is going to be letter C, so I got 9570 joules is my total. So he starts out high up on the hill, 15 meters high, and he's moving at 5 meters per second. So we got a double whammy here. We got the total is the 2. So I'm going to put a star by this one because an asterisk, because we got it's this is like the total. This is what we're starting with. And the thing to keep in mind is once you find the total at some point, that is going to be the total everywhere. So this number right here is going to be our big, like, helpful little number that we know, because it's going to be the total mechanical energy everywhere on this little situation. Okay, so now we got this magic number that's going to help us figure out a lot of other questions. Okay, so once you figure out the total at one spot, that is going to be the total at all the spots. All right, so it kind of goes on from here. I'm not going to necessarily get through this, or I'm going to get through it, but I'm not going to stay too long on this. But now we've got a new height. It wants to know the potential energy with a new height of 10. All right, so I'm just going to tell you, because you can check the key on this one, but the answer to this is 5880. I mean, let me really quick explain how I got it, but basically it wants to know the potential energy, gravitational. So we're going to take the skater's mass of 60 times 9.8 times the 10 meters tall. You don't have to worry about anything else. It's asking a straight up question. What is the potential energy? And it gives you a height. You just do that. You just multiply it. Okay, don't overthink it. Same thing with number E, letter E, except it's asking for the kinetic energy. All right. But then you go look, it's like, oh wait, it doesn't give us the speed. Well, what does it do? What do we know? Remember that total mechanical, 9570? Well, guess what? At every single point, at 10 meters tall, at 10 meters and everywhere else, the total has to be 9570. So all we got to do is take our 9570 joules, subtract our 5880, and our total is going to be 3690. So, all right, that's it. So that's, if it doesn't give you, like, if it asks for kinetic energy but it doesn't give you velocity, look to see if there's another way. All right, and like I said, in this case, these two have to add up to be the total. So we knew the one, we knew the gravitational potential energy, and so we know that in addition to the kinetic energy has to add up to the total. Okay, and number 5, F, number F sort of drives that point home. What's the total mechanical energy? Well, what did I say about total mechanical energy? You don't even have to have a height here. It says a height of 10, but it doesn't matter, because the total mechanical energy is never going to change as long as there's no friction, which I guess, yeah. Anyway, the answer is going to be 9,570 joules, because it's never changed. There's not really any math to do, all right? Because it doesn't change. So that's all there is to it. And then we go on. What's the potential energy at the bottom of the ramp? So there's not very lot of space here because it's the bottom. And so there's not, if you just think about it a second, well, if it's the bottom, it's got no height, and it's got no height, Oh, well, then it's got to be no potential energy. Moving along. What's the kinetic energy at the bottom of the ramp? Well, okay, 1/2 mv squared. Oh, wait, there's no velocity given. Wait a minute. What do we do here? Well, we know that the potential energy at the bottom of the ramp is 0. And we know the total is 9570. Oh, well, that's easy then. The answer is 9570 because at the bottom of the ramp, the total is still going to be 9570. And we've got 0 here, so the kinetic energy must be 9570. And again, just to sort of drive the point home, what's the total mechanical energy at the bottom of the ramp? Well, 9570. It never changed. All right, now I'm getting sloppy, but that's the point. No, that's not the point. The point is it never changed. And now we get to a real question. What's the velocity at the bottom of the ramp? Okay, this is what I was talking about earlier. We know the kinetic energy is 9570. And we know kinetic energy is 1/2 mv squared. And if I was trying to solve for velocity, I would have to rearrange all that. And so I've already done that. So I'm just going to kind of peek back and be like, well, velocity, I know it's going to be a square root of kinetic energy. And then I look again. And I've already got it written down somewhere. So, you know, I don't have to do this every single time. And there's my equation I'm going to use to get velocity. I know the kinetic energy, 9570. I just have to plug that in. And once again, a lot of trouble comes from the calculator here. The calculator has to know to do the bottom part first, then divide, and then take the square root. So what I would recommend in your calculator is parentheses there, and maybe use 0.5 instead of half, and then another set of parentheses up here. Okay, and that way it will do the math on the bottom first, and then it will do the math in the inside next, and then it will take the square root of that. So try it, check the key. Well, I'll just write the answer down. It's not a big deal. J, I got 17.86 meters per second. If you get 17.86, you did it correctly. All right. You got to make sure you got the right numbers and all that in there, but the kinetic energy, you know, the mass is 60. But plug that in the calculator, make sure you're able to get that. And if not, let me know. I'll see what I can do to help you out. All right. Now we get to some friction. The question wasn't worded very well, because up to this point we kind of did ignore friction. But why didn't the skater get to the same height? Well, the answer is friction. And there is friction, and friction turns that kinetic energy into heat. And heat is another type of energy. It's the fourth kind, thermal energy from the energy skate park. And it's just lost. Okay, it's not destroyed. It's just changed into heat. And so it can't be used anymore. It's not stored. It's not used for kinetic. It's not used to move anything. It's just changed to heat. And it's lost. Okay, it vibrates molecules, and that's what we call heat. But I don't want to get into that right now. Okay. So HIJKL, question L, what happened to velocity as she traveled downward? That's just sort of keeping in mind, well, as she traveled downward, she's going to get faster. That's what things do when they travel downhill. But why? In terms of energy. And it's because I'm writing this kind of backwards. That's just ignore that. PEG becomes kinetic energy. Now that's not the full explanation. That's just going to be, you better write more than that, because you gotta explain, and I'm just going to explain it in words, but you need to write more than this. The gravitational potential energy that he had at the top of the hill becomes kinetic energy, and so because there's more kinetic energy, that means he's going to move faster and faster and faster. Okay, and conservation of energy means that the energy is not lost; it just changes from gravitational to kinetic. All right. All righty. Last thing, a little bit about the bar charts. Honestly, just kind of make sure you can do this. Look at M, that's not the bar chart, but make sure you're able to do that. If she pushed with 3 times the velocity, just check the key, all right? It's going to explain. She's going to have 3 times the starting kinetic energy, but she's going to have the same amount of potential energy to start with. Look at the key, ask me questions, all right? But this only affects the kinetic energy of it. Looking at N, the skater's energy at the top of the ramp. Let's just pick a total. It doesn't matter what it is. All right, that is very sloppy. And so do as I say, not as I do. Maybe use a straight edge for yours. But we do know that she's got a lot of potential energy at the top, but it's not all potential. She does give herself a little bit of a boost. So that little bit that's left over that I didn't quite get to the top, that's going to be taken care of by the kinetic energy. So she gave herself a little bit of a boost. These two together need to add up to be the total. And that total will never, ever, ever change. All right. What might happen is you might get some thermal energy, and that takes away some of the energy from it, but not from the total, just from these other two. These other two like to change. The total does not change. Check the key. Go back and look at the energy skate park thing. Talk to me in class tomorrow if we need to, and we'll take care of that. 19. I'm going to touch on that really quick and then probably end it. It's the whole idea of total energy not changing. So if you know the total at one point, 30 plus 0, then you know the total at every other point. They should always equal the same number everywhere. All right, this is a pretty terrible drawing that made quickly, but you got to swing them back and forth. Once you find the total at one spot, you find the total everywhere. Okay. Number 20 and a couple of the other ones, well, those are kind of using the same exact thing. Once you find the energy, the total energy, in this case for number 20, we're including some elastic energy now, but it's got elastic energy. It's down at the ground, so the height is 0. So I'll just write h is 0. The velocity is 0. So that should tell you right away that there's no gravitational potential energy. There is no kinetic energy, but it does tell you about the elastic energy. So once you figure out the total mechanical energy, the total mechanical energy doesn't change. So once you figure out what it is, it's going to stay the same at every other point. So it's kind of similar to some of the, like the question that we did with the skater. Okay, once you get the total energy, excuse me, then it doesn't change. All right. I think I'm going to call it. We'll work on the note card in class. I'll give you a note card and you'll be able to write down whatever you want. I'm just going to put this back up here because I feel like this is probably the bread and butter of this whole unit. It's like I said, if you can master these 3 equations, then you're going to do pretty well. Okay, these 3 and understanding that the total energy never changes. So these 3 equations are going to be like the energy is always going to be like being passed back and forth between these 3 types of energy. And so if you can just work with them, you're going to be good with this. All right. So let me know. There were no questions in the chat, and that's fine. But just let me know. You can still use a Remind app. That's basically it. So I think I'm going to wrap this up. And let me know if I could help you with anything else. Okay. Take it easy and study hard.